Okay, now we're going to consider energy. For now, we're going to assume that energy is conserved. There are no non-conservative forces doing work, so there's no friction or air resistance acting. The energy is going to be converted between potential energy and kinetic energy, but the total energy should remain constant, as we're not losing any of it. Okay, so we know that kinetic energy is equal to a half mv squared, and we've shown that v is equal to omega a sine omega t plus phi. So just substituting that expression in for v, we end up with this expression for our kinetic energy. And the potential energy stored in the spring is given by a half kx squared, which is a half k a squared cos squared omega t plus phi. This is just substituting in for our x. Okay, so to get the total energy, we just need to sum the kinetic energy and the potential energy. We can take a squared out as a common factor, and then we can make the substitution omega squared is equal to k on m. So substituting that in, we end up with this expression. We can pull k out the front, and you know that sine squared theta plus cos squared theta is equal to 1. So replacing this sine squared omega t plus phi plus cos squared omega t plus phi with 1, we end up with the total energy is a half ka squared. Okay, these graphs show you the relationship between the potential energy and the kinetic energy. For this one, we've got the energy versus time graph. So when the kinetic energy is minimum, the potential energy is maximum. And you can see they're just inverting there. With this graph, we've got the displacement versus the form of energy. Now, when it's at its equilibrium position, it's got its maximum velocity, and so it's got its maximum kinetic energy. At the two ends of the motion, its displacement is equal to the amplitude. It's just starting to change direction, so its velocity there is 0. And so it's got no kinetic energy, and all its energy is stored as potential energy in the spring. So this is just another way of showing you that information. When it's at its maximum displacement, all the energy is stored as potential energy. When it's at its equilibrium position, it has its maximum velocity, but it hasn't stored any energy in the spring, and so it's got maximum kinetic energy, and so on. Now we can use this to work out the velocity given the position. We've got that the total energy is a half ka squared, and that's equal to the kinetic energy, a half mv squared, plus the potential energy, a half kx squared. So solving this, we can cancel out all the halves as a common factor, and we end up with mv squared is equal to k, it's a common factor between these two, a squared minus x squared, and so dividing through by m and taking the square root, the velocity is equal to plus or minus k on m, a squared minus x squared. K on m is just omega squared, so pulling omega out the front, we've got the velocity is equal to plus or minus omega a squared minus x squared. Now this actually makes it much easier to solve some problems. Let's just have a quick look at the last problem we solved. Part C here, to work out the velocity, we had to start by working out the time, which was quite tedious. Another way to do it is to use the expression that we've just derived, that the velocity is equal to omega root, well, if there's a plus or minus, a squared minus x squared. Okay, so we've got plus or minus omega, which was 4. The amplitude was 0.100 squared. We were told that x, it was 6 centimeters from the equilibrium, so that's 0.06 squared. Solving this on the calculator, we end up with plus or minus 0.32 meters per second, which is what we got here. So that's a faster way of doing it. Okay, so that's all the new material. Now we're going to look at some problems that we can solve with these equations. Okay, so an object spring system moves with simple harmonic motion and has an amplitude A. When the kinetic energy of the object equals twice the potential energy stored in the spring, what is the position x of the object?